Pleasure to welcome you today. As I'm sure you all realize, this is an experiment for us. All of us have been involved, all of us who've been involved in organizing this have been involved in summer schools before, but this is the first time that we do it online. We miss those conversations that we would have in between the lectures or over lunch or something. On the other hand, it is quite remarkable to be able to reach all the way around the world. And a special thanks to those of you who are joining us from less comfortable time zones. So thank you. As you know, it's a series of lectures covering a wide range of topics in the theoretical sciences. The format is simple. Each lecturer will have 2 blocks of 2 hours to use as they see fit, and we will be learning as we go along what the best way is to use that time. Our first speaker is Vladimir Rosenhaus, who is a member in the School of Natural Sciences at the Institute for Advanced Study. Vladimir did his PhD in Berkeley, spent few years as a postdoctoral fellow at the Kavli Institute for Theoretical Physics in Santa Barbara. He has done marvelous work on this interface between quantum field theory, chaos, gravity, and so on, where many ideas sort of mix together in ways that have been very exciting. We're also very excited because he will be joining us as a faculty member at the Graduate Center of the City University of New York very soon. And so this is his, I guess, first official act as a faculty member at the Graduate Center. It isn't obvious how to, actually, sorry, before launching into things about the day, let me also give a special thanks to Goen Minshall, who has been crucial in making all of this happen. You know, it's tempting to think that in a virtual event there isn't any real organizing to be done, but I think you all know that that's not true. And so our thanks to her. For the proceedings, I think what Vladimir has decided, and he can tell you more about this, is that you should raise your hands when you have questions, just as you would in a lecture hall. With more than 200 of you, it's a little more challenging, and so all the lecturers will be figuring out how to do this. But let me ask, if you haven't done this before, take a moment to figure out how you raise your hand. And for the rest of the time, you should stay muted. I see that, yes, people are experimenting. An important part of raising your hand is remembering to lower it once you've been called on. You are, I think, very welcome to have your video on so that Vladimir has the sense that he's speaking to more than a collection of tiles. On the other hand, at some point, we may discover that there are bandwidth issues and recommend that people turn their videos off. We'll see how this goes. Without further ado, Vladimir on classical and quantum chaos.
Thanks, Bill, and thank you for coming. So the talk will be on few body and many body chaos. So the format, which Bill just said, so there'll be a break from 11:50 to 12. So you can either just take a break and get some food or ask questions. And I'll also occasionally pause to check if there are questions about every 15 minutes. And during the questions break, please raise your hand. To raise your hand, you click on More in the bottom panel and select Raise Hand. And I will then call on you. And as Bill said, please keep the microphone muted at all other times. And the second lecture will be tomorrow at the same time. Also, the lectures are being recorded and they'll be placed online, and you'll be able to find the slides online as well. In fact, the slides for this talk are already online. So as an introduction, it seems relevant to ask, is chaos relevant? Classical mechanics has been around for centuries, yet this will be a lecture about mechanics and developments that occurred within the last 50 years. And quantum field theory, the content of the second lecture, has been around for a century to some extent, yet many of the developments we will describe occurred in the last decade. And so it's very reasonable to ask why it took so long. As a way of explanation of why it took so long, we gain intuition by solving simple problems, harmonic oscillator, two-body problem, and so on. More precisely, the systems we are familiar with are integrable, which means that they have enough conserved quantities to allow us to easily solve the equations of motion. And of course, we realize that integrable systems are not generic. We realize that when we learn fresh things, but we have our minds, and sometimes explicitly, hope that everything else can be solved at least approximately by doing perturbation theory around the interface. So that's by way of explanation of why we seem to think we can get by with integrable systems. And indeed, in introductory physics, there's an extensive discussion of the two-body problem, but then little mention of the three-body problem. And the reason seems clear, that the equations in the three-body case are much harder, and it wouldn't seem fair to ask a freshman to solve them. But in fact, the three-body problem has no closed form solution. That's not obvious, but it's a true statement. But perhaps even knowing that, it's unclear if this fact is a physical relevance, that there's no closed form solution, or is it more just of a mathematical curiosity? Because in any case, we seem to have a good sense of the motion of the Earth, Sun, and the Moon. We can easily solve explicitly for how the Earth moves around the Moon, assuming there's nothing else, and we know how the Moon orbits the Earth, and so on. And in our heads, we combine the two together, and it seems to be working fine, even though we can't solve it exactly. So that's an explanation for why we seem to not need chaos. On the other hand, once one moves up to sophomore level physics and learns statistical mechanics, we need to solve for the motion of a large number of particles in a box. And at that stage, we claim ignorance. We never solve for the motion of a large number of particles in a box. We say the system is so complicated that we are safe to assume that even though we took the particles to initially have definite positions and momentum, they are equally likely to be anywhere. So we replace specific initial conditions, very concrete initial conditions, with a microcanonical ensemble, like for this box of gas here. And on first thought, this sounds like a reasonable assumption. Why does it sound reasonable? Well, visually, it's fairly clear that to draw this picture, it doesn't really matter which initial conditions I take. The picture will always be different, but roughly look the same. But on the other hand, dynamically, we have little understanding of how this is achieved, why it's justified to replace specific initial conditions with the microcanonical ensemble. Indeed, in mechanics, when we were discussing mechanics, we said the trajectories move on periodic orbits, and those pass through a small fraction of phase space. As we'll discuss more, integrable systems only explore a very small fraction of phase space. On the other hand, now we're saying that a single trajectory moves through all of phase space. And indeed, in statistical mechanics, the assumption of molecular chaos is used to justify ergodicity. And so from this discussion I just gave, one may be led to draw two conclusions. The first is that chaos is only relevant to many body systems, because few body we can sort of solve, we think. And in the many body case, the equations are so complicated that it's not surprising we have little understanding of the dynamics. And the second conclusion one might want to draw is that in highly chaotic many body systems, perhaps such as a box of gas or the weather, we can't calculate or predict much anyway. Everyone knows we can't predict the weather a month in advance. So it seems like, again, there's not much for us to study, because if we can't calculate anything, there's little for us to do. So in fact, both of those conclusions are false. Chaos occurs in few body systems, as we'll see, and it even occurs in some of the simplest conceivable discrete maps. I think historically people found this surprising, though I'm not sure. And the second conclusion is also false. There is in fact a lot that we can calculate. We just need the right tools and the right questions. And chaos is, at least theoretically, far more generic than integrability or near integrability, and it has proved relevant in a broad range of applications. So the outline, this is the outline for the first lecture. We'll first discuss classical few-body chaos, start with the Lorenz model. The Lorenz model is the famous picture of the butterfly wings, which introduced the butterfly effect. Lorenz was trying to understand the weather, came up with a simple model, and numerically solved it on the computer in the 60s. And to his surprise, discovered chaos, and I guess that led him to conclude that the weather is not predictable. From Lorenz, in fact, discovered that one can simplify even further and come up with discrete maps, much simpler maps, which also exhibit chaos. And so we'll discuss discrete maps a little. Then we'll turn to pinball scattering. Pinball scattering is like a game at the pinball machine. There are several discs, and you throw a ball in, and then it can bounce around the discs and go out. This too is an example of chaos, and a simple one. It's useful to study because of it's a simpler version of many particles scattering against each other, which is one of the things we're ultimately interested in. And the final topic in classical few-body chaos is the KAM theorem, and that's to address the question that we posed already: how does one get from integrability to chaos? In one case, motion in phase space is on a torus, a very small subregion of phase space, whereas for a chaotic system, it fully explores the phase space, and so there needs to be some way of going in between, which appears puzzling. So the KAM theorem addresses that. Then near the end, or perhaps in the second lecture, I'll briefly discuss quantum few-body chaos. In the second lecture will be about quantum many-body chaos. I will be skipping classical. The natural thing after classical few-body chaos would have been classical many-body chaos, but I will be skipping that for reasons that I will explain. And for quantum many-body chaos, one of the main things I'll be describing is the SYK model. So it's a recently discovered model. That's a simple model of quantum many-body chaos, which perhaps in 50 years will be like some of these models as a prototype of chaos. And I'll describe quantum bounds on chaos and how chaos occurs in black holes. The last topic is surprising. On first thought, we'll discuss it more to give you a preview. Black holes are black only classically. Quantum mechanically, they emit Hawking radiation, which is thermal radiation. And so one expects, one has the intuition that if one has a thermal system, then that is ultimately due to chaos. And it's been known for half a century that, since the work of Hawking, that black holes behave like thermal systems, and it was always an open question of where the chaos is. And that was only recently discovered, and that led to much of the interest, at least within high energy, in these quantum many-body questions. Another comment is that each of these sections is, for the most part, self-contained. So if you feel like not paying attention to one, you can somewhat easily jump into the others. So let me now pause to see if there are any questions. So you can ask a question by raising your hand, and then I'll call on you. No questions, or no one knows how to raise their hand?
I'm not really sure how to raise my hand, but is that Alexi's model you're talking about? Is that right?
Correct. SYK stands for Shastev Yekataev. Yes. Any more questions? Okay, I guess I haven't said much yet. So as a warning, in this lecture, we will touch on a range of topics, all of which are a small subset of well-developed fields that have been around for decades, and they're discussed in many books, which is where I learned them. And I have no insight to add, and my knowledge is quite limited. In the second lecture, we will discuss topics that were developed in the last 5 years. These I understand better. However, they're only a small piece of quantum any-body chaos, a field in which most of the major questions are still unanswered. So before starting with the topics in the outline, it's good to keep in mind some major questions which we won't answer, but have been motivating questions for decades. The first is the question of turbulence. Feynman is sometimes quoted as saying that turbulence is the most important unsolved problem in classical physics, though I have never found where he said that. So the question can be formulated in a precise manner. And so suppose one creates a turbulent fluid by continuously stirring it. And then one wants to measure correlation functions of the difference in velocity between 2 points. So the question is, what are the correlation functions? And by correlation functions, one means that one does a spatial average. So you measure the difference in velocity between this point and that point, and then you average over space. So we're not asking the kind of question that we don't think we'll be able to answer those on specific initial conditions. What's the outcome? We're going to ask statistical questions like we do in statistical mechanics. And Kolmogorov in the 40s came up, he assumed scale invariance and came up with some very simple power law answers for the correlation functions. And those simple answers are mostly correct, but experimentally they're not precisely correct. They undergo corrections, and it's been a long-standing open problem to compute the corrections and what precisely the correlation functions are. A second question one might be interested in is a microscopic derivation of transport coefficients. So suppose one is interested in the diffusion coefficient of some system. One starts with a Lagrangian. It could be a classical or quantum system, and one just wants to compute what the diffusion coefficient is without having to measure it. A third question is a theory of thermalization. So we expect that integrable systems do not thermalize. On the other hand, many systems that are thermal do thermalize, and there are a number of precise questions. Suppose you perturb the system, such as by a quench. How does it relax back down to equilibrium? How rapidly? How does the entanglement entropy grow? And so on. For all of this, one needs a theory of how this occurs, which presumably ultimately requires an understanding of many-body chaos. And finally, another question that has been around for half a century is to redo Hawking's calculation of Hawking radiation, but obtain an answer which is consistent with quantum mechanics, an answer in which information is not lost. This will describe somewhat at the end of the second lecture. All right, any questions about the questions? Okay, good. Let's move on. So I'll start with the Lorenz model. So in the 1960s, Lorenz created a simplified model for convection rolls in the atmosphere. So in the end, his model consists of a coupled set of 3 nonlinear differential equations, 3 variables x, y, and z. X dot is sigma y minus x, y dot is rx minus y minus xz, and z dot is xy minus bz, where sigma, r, and b are some constants. Depending on the constants, there's different physical behavior. So 2 things to notice. The first is that the equation is nonlinear. There's an xz term and an xy term. In addition, the system is dissipative. Phase space volume contracts, which is, depending on one's background, a bit different from what we're used to, but that's fine. So that was the system he wanted to study. Good. So to quote the book by Gleich on which describes some history of chaos, Lorenz took a set of equations for convection and stripped it to the bone, throwing out everything that could possibly be extraneous, making it unrealistically simple. Almost nothing remained of the original model, but he did leave the nonlinearity. To the eye of the physicist, the equations looked easy. You would glance at them, many scientists did in years to come, and say, I could solve that. Yes, Lorenz said quietly, there is a tendency to think that when you see them, there are some nonlinear terms in them, but you think there must be a way to get around them, but you just can't. So Lorenz's goal was to understand those equations. So what he did is he numerically solved them. And here are some plots taken from the book by Strogatz. The plots are identical to the ones in Lorenz's paper, but they're of higher resolution. So he picked some parameters for sigma, b, and r, and then picked some initial conditions for x, y, and z. And the plot is just y as a function of time. So we're not, so x and z are also something, but we're only plotting y. And the thing to notice is that it looks completely aperiodic. In some regions, it looks like it repeats, like this looks like these three things look the same, but if you look closely, they're not. And these also look the same, but if you look closely, they're not. And if you keep running for longer and longer times, it continues to look aperiodic, which is unexpected from everything we normally learn in mechanics. So another plot Lorenz has is now a two-dimensional plot, now of both x and z, and the plot is the famous butterfly wings. This is the motion in phase space for those initial conditions. So it goes like this, loops around, then loops around, and so on. On the figure, the trajectories look like they cross, but they, of course, do not cross. It's just an artifact of drawing in 2 dimensions. So the result has several remarkable features. The first is that after some initial time transients go away and the trajectory settles down to motion along the butterfly wings, just these 2 wings. The wings are almost 2-dimensional, but they're in fact slightly more. They're actually a fractal, and so this is what's known as a strange attractor. The second feature is that each trajectory can, to a good approximation, be described by the sequence of which 2 wings it orbits around. For instance, one can specify L, L, R, and so on, where L and R stand for the left and right wings. There's little else happening here except just saying how many times you orbit this wing and that wing and so on. And finally, its chaotic trajectories from nearby points are both diverging from each other, which and at the same time they're remaining in this confined region of phase space. And it's really those 2 things which are the hallmark of classical chaos, stretching, which is the diverging, and folding, which is necessary to stay in a confined region of phase space. So that's nice, and I think everyone is familiar with that picture. But Lorenz went further. So he went back at this 1-dimensional plot of z as a function of t, and he wants to simplify. So he's just going to look at the peaks. So this is zn plus 1, and so on. So he's going to label each peak and record that. And what he noticed is that, to an excellent approximation, the value of zn, the local maximum, predicts the value of the next local maximum. So this is surprising because the same value of Zn can occur many times, or approximately the same value, and it's a priori, one would not expect that would predict that, having known Zn once and being able to know Zn plus 1, that when the same value occurs much later, you will again know the next one that occurs. Lorenz found that it does. So what he did is he made a plot of Zn plus 1 versus Zn. And the plot looks like this. So these are data points, Zn plus 1 versus Zn. And this plot has essentially no thickness, which indicates that it's a function. If what I would have expected without knowing anything is that there would be significant thickness, so that for the same value of Zn, there will be multiple values of Zn plus 1, but in fact, it's essentially a line. So that's the first thing, it's a function. And the second thing is that the magnitude of the slope is greater than 1 everywhere. As you can see, this is the 45-degree line. And so that means the Lyapunov exponent is positive. So to appreciate how surprising this must have been, again, to quote Blike's book, he says, for the first time, Lorenz's pictures had shown what it meant to say this is complicated. All the richness of chaos was there. At the time, though few could see it, Lorenz described it to William Malkus, a professor of applied mathematics at MIT, a gentlemanly scientist with a grand capacity for appreciating the work of colleagues. Malkus laughed and said, Ed, we know very well that fluid convection doesn't do that at all. The complexity would surely dampen out, Malkus told him, and the system would settle down to steady regular motion. Of course, we completely missed the point, Malkus said a generation later. In fact, Lorenz's paper, as far as I understand, had almost no citations for the first 10 years. Of course, now it has tens of thousands of citations. Good. So are there questions? Could someone at least raise their hand so we know? Good. So Omar, do you have a question, or that just to test?
Yes, I have a question.
Good.
So in the first slide, you said that the Lorenz model is technically dissipative. So yes. That means that the phase space volume contracts. So yes. Can we think about it in a way that the momentum keeps getting smaller and smaller till it becomes a point? So that's how it contracts, like something like that?
So I think I would have thought of it as the fact that we're. I would have thought of it as the volume is the fact that the volume is contracting. You can see in the fact that one is approaching this attractor. So you start out anywhere in phase space, and then, as we saw in the trajectory, you quickly approach. So you start off somewhere here, but then you quickly approach this pair of butterfly wings, the strange attractor. I guess it's important to note that chaos occurs in non-dissipative systems as well.
But that has something to do with the energy being lowered, that it decreases, yeah?
The thing, well, the thing that the volume here is is XYZ. So we're going to define energy as X. I'm not sure. How are we going to define energy as X dot squared plus Y dot squared plus Z dot squared plus? I'm a little at a loss of how to define energy because it's not like Newton's laws.
Okay. Thank you.
Sure. Pedro?
Can I ask a question?
Oh, yes.
That curve of Zn plus 1 versus Zn.
Yes.
The Lorenz, yes.
Yes.
Yes, the next curve, actually.
Yes.
Yes. Is there any analytic solution or any try to find this functionality as an analytic function since Lorenz up to now? Or it's only a numeric calculation? Is it possible to find any analytic solution for this curve?
Good. I guess we could fit the curve, but perhaps but then there are many possibilities. Perhaps your question is from the original. Perhaps your question is from the original differential equations. How would one
Yes,
both figure out
yes.
that.
I was curious if anybody has tried to find any approach at least to find some sort of analytic
That's a good question.
approximation or solution.
I'm not sure. I'm not sure.
Okay.
Yeah.
Thank
Does
you.
anyone know the answer? Okay.
It potentially means there has not been any.
Sorry, I missed the question. What was the question?
The question, well, I strengthened the question starting with the Lorenz differential equations prove that that Zn plus 1 versus Zn is essentially a function, though it's not precisely a function, and find that function.
Okay, I don't remember. Or maybe I never saw it. Okay. No, sorry, don't know.
Okay, thank you.
Sure. Pedro is next. Oh, that was Pedro.
Yeah, could you, no, it's okay. Can I ask a question? Yes.
Yes.
Could you go back to the plot of the Lyapunov exponent of the same plot as
Yes.
maybe I'm misunderstanding the plot. You said that the magnitude is always greater than 1, but then the slope decreases, right?
The slope d. So here it's greater than 1. Here it's still greater, and here yeah, it's always so. Can you say more?
Yeah. Sorry. In the second part, the slope begins to decrease, and it's no longer above the 45. Yeah, it's no longer above the 45 degrees. So maybe I'm misunderstanding what you're saying.
But the magnitude is still big.
Oh, okay. I understand. Okay. That did.
Okay. Any more questions?
Yeah.
Yes.
I raised the hand.
Yeah, you raised your hand. Yes.
Yeah, so just a comment. The answer to Pedro is yes. So the Lorenz model, well, he was doing this numerical simulation, but later there was two approaches, one done by Guggenheimer and William, and there was another approach by Aframovich. They built what is called a geometrical Lorenz model. So it's a geometrical construction that in principle is not resemble the equation by Lorenz, but where you can prove analytically, and you can prove that the solutions are actually chaotic, and actually they have the one-dimensional model that Vladimir was describing. So actually this picture by Vladimir for the geometrical Lorenz equations, or the geometrical Lorenz model, is true. And later in the 98, it was proved by Tucker that the Lorenz equation are a Lorenz geometrical model.
Excellent, thank you.
So this can be, so this, whatever you are seeing is not just numerical simulation, it's actually analytical proof, and the graph that you show, yes, is actually a real graph, and this can be done explicitly. And this was done in 98 by Tucker. Basically, first he do some kind of computational approach to prove that there is a geometrical model that describes all the situation.
Good. Okay, any more questions, comments? Yes, Armin?
I wanted to ask, in this Lorenz model, we see that this chaotic behavior is correspond to this fractal attractor. Is this a universal behavior for chaotic systems, or this just happens for this kind of this Lorenz system?
If it's dissipative, then it's broadly universal. In fact, it's surprising. So when we discuss, so one might think that the viewpoint I used to have was I don't really care about dissipative systems because that's not what we normally study. However, what's interesting is that in the example of scattering, the pinball game that we'll describe, so that's not a dissipative system. That's like the kind we're used to, Louisville and so on. there's instead of a strange attractor, there's a strange repeller, which is the surface of trajectories that stay confined between the disks and that never escape. So there's a very similar concept there. So it's indeed, it's broadly universal.
So can we say that if we have chaotic behavior, certainly there would be a fractal strange attractor in this system? It's one-to-one, or there are exceptions?
I wouldn't say that. I wouldn't say that.
Okay, thank you.
Yes. Okay. Next, Avni.
Yeah, hi. I wanted to ask them that when you said that the system is dissipative and the phase volume decreases, is there a cause and effect relation, or are you just stating them as two independent or observable?
I was just saying the phase space volume with time is decreasing, and hence it's being called dissipative.
So you didn't mean dissipative in terms of the energy as such.
That's right, but it's easy to show that. That's right. One doesn't, but here one is just working with the variables x, y, and z. So in those variables, it's easy to show that that volume, the one in terms of x, y, and z, is contracting.
All right. Thank you.
Yes, Saeed?
Yeah, I think you showed that this system has a transient regime in the beginning.
Yes.
Is there like a set of parameters that can cause this transient regime to be, I mean, the time interval of this transient regime to diverge? So basically, we work with a set of.
I see what you mean. You choose initial conditions such that you just escape away, and you never get this behavior.
Not necessarily initial conditions. I meant more like parameters.
Like the, I think so. So depending on, it's only for, so depending on the sigma b's and r's, one can get a whole range of things. Yeah, I don't know which sigma b and r will do what you said, but there probably are some. I'm not sure. Yeah.
Okay, so in principle, it could be that the equations are effectively deterministic, even though that we know that there is an underlying chaos, but it takes so long that we never see it.
Let's see. So if we choose particular values of sigma b and r, like small ones, then the system is not chaotic; it's integrable.
Right. Okay.
And once that's happened, so then there are parameters in between where various things can happen.
Okay. Thank you.
Okay. Let's move on to discrete maps, and then we'll take the 11:50 break. So this will be a very simple section. So the thing one of the takeaways from Lorenz's study is that instead of a set of differential equations, we can already see chaos at the level of discrete maps. And the fact that the discrete map occurred for the differential equations motivates studying the discrete maps, whereas otherwise one might be suspicious if they're physically relevant. So one of the simplest is the tent map. So now we're just going to be inventing maps of xn plus 1 versus xn, which we analytically know because we're going to invent them. So this is the tent map, and it exhibits the prime feature of chaos of stretching. So the interval from 0 to 1/2 is stretched to 0 to 0 to 1. So if the point started anywhere in between 0 to 1/2, it then ends up anywhere between 0 and 1. And it also exhibits folding, meaning you bring the same region, bring everything back to 0 to 1. But the folding is a bit of a cheat here because the map is not 1 to 1, because 2 points get mapped to any 1 point. But that's just an artifact of 1 dimension. So we simplified too much in some sense. So the stretching is what causes nearby trajectories to diverge, indeed by a factor of 2 on each iteration. And to make this obvious, if it isn't, all one has to do is just iterate the map several times. So here's a plot from before, xn plus 1 of xn. Now I just plot xn plus 2 of xn. So that has 2 spikes, xn plus 3 versus xn, which has 3 spikes. And so it becomes clear that initially if I ended up within some region of, say, 1/2, I knew xn plus 1 would be somewhere around here. Whereas here, if I'm within this same region of 1/2, xn plus 3 can be in a much broader region. So this is the prototype of chaos, the stretching. If that wasn't simple enough, we can construct an even simpler map. So it will become clear why we're trying to simplify. So an even simpler map is this map, xn plus 1 is equal to 2xn mod 1. So pictorially, it's this. So you double xn, but then bring everything back to be between 0 and 1. The reason this map is nice is that we can represent the initial conditions as a binary decimal. So the initial conditions, we start with some value of x0, and instead of writing it in the normal way so it's some number between 0 and 1. So instead of writing in the normal decimal expansion, we write it in binary, so in powers of 1/2 to the j. So aj here is either 0 or 1. So x0 is like 0.01, 001, so on. So that we can always do. We're just representing the initial condition in this way. And the point of doing this is that now the map takes a very simple form. The map xn plus 1 equals 2xn mod 1. All it does is it shifts the decimal 1 to the right, and you discard the thing to the left. So if this was x0, dot a1, a2, a3, a4, once you apply the map, you get x1, which is dot a2, a3, a4, and so on. And now it becomes very clear that a small change in initial conditions, say you change the nth digit after the decimal, which is a very, if you change the 10th digit after the decimal in x0, that's an extremely small change. It's clear that after 10 iterations, this will become a large change. Because after 10 iterations, the 10th digit after the decimal will become the first. And this brings us to another famous example of famous discrete map that's an example of chaos, which is the Baker's map. So it's slightly more elaborate, but not much. Now it's in 2 dimensions, and the map consists of, so this is the map, and pictorially it has 2 steps. So first we stretch in the x direction by a factor of 2 and contract in the y direction by a factor of 2. So that's this step. So we stretch, this goes from 0 to 1, we stretch to 0 to 2, and then we contract in the y direction. Then we make a cut through the center and place the right half on top of the left half to get this picture. So this sequence of pictures just corresponds to this map. And again, we can do the same thing we did with the Bernoulli map. We represent x and y in this expansion in powers of 2, the dyadic expansion, in terms of AIs and BIs, and we combine the two. So now the B's go to the left of the decimal place and the A's go to the right of the decimal place. And now one can easily see that the action of the Baker's map is just a shift of the sequence by 1 to the left with respect to the decimal place. If you just plug in this into this expansion, you'll see what I said is true. And so what's these maps are nice because so one thing we saw in the Lorenz map is that the trajectory in phase space is complicated and specifying it is complicated, but then we saw that to a good approximation, there's one can just give a sequence of L and R to specify the trajectory. You just give the sequence of how many times you orbit each wing, the sequence of what that happens, that's going to be called the symbolic dynamics. And so in effect, instead of to specify the initial conditions, you might think you could just say, okay, this is going to be the sequence of how you orbit the 2 butterfly wings. You just specify the initial conditions as L, L, R, and so on. So in these maps, we can make that precise. And we'll see something similar in pinball scattering. Good. So I'm going to skip the logistic map. So the logistic map is another one-dimensional map, which is more elaborate. But I will skip that and give a summary of discrete maps. So Lorenz came up with a simplified. So we started off, both we and I think historically, by wanting to understand the weather, complicated many-body system. And Lorenz came up with a simplified model having only 3 variables, and the motion and phase space was on this pair of butterfly wings. Lorenz then found he could form a one-dimensional map by looking at the local maxima of z of t, which are like over here. And he then made a map of zn plus 1 versus zn, and found to a good approximation that it behaves as a function. And it in itself exhibits chaos. And then we discussed some simple one-dimensional maps. The logistic map, which we did not discuss, but we discussed the 10th map, which is this one, the xn plus 1 equals 2xn mod 1 map, and the Baker's map. And these are all examples, simple illustrations of stretching and folding that's a hallmark of classical chaos. And to end, I'll quote this paper by Artuso, Orell, and Svetanovich. They say the insight of modern dynamical systems theory is that the 0th order approximation to the harshly chaotic dynamics should be very different from those for nearly integrable systems. A good starting approximation is the linear stretching and folding of a Baker's map rather than the winding of a harmonic oscillator. All right, thank you. So let's take, those who want can take a break, and the rest we can discuss in questions. And we'll resume the slides in 10 minutes. Good, so are there questions? Yes, Enrique?
There was one comment that you were doing about how universal are those models, no?
Good, yes.
Well, there is this notion of topological entropy. And
yes.
You will wonder is like, if the system have topological entropy that is positive, are you going to see one of those models behind? Well, the answer is yes, at least in lower dimension. So when the entropy is positive, you have something that the people call in mathematics the horseshoes, which is basically some kind of property where you see that the cube that is stretched on one direction contract and the other unfold it back. And so in other words, if you have like a chaotic system and you describe it by the entropy, so you have the positive entropy, yes, you're going to see one of those geometrical models.
Good, thank you.
So there are certain universality.
Other questions? Yes, Joshua?
Yes. What physical system could be modeled with the Baker's map?
The specific Baker's map, I think nothing. It's too simplified.
Well, there is one particularity on the Baker map that they have this discontinuity. In the way that you wrote the Baker map is volume preserving, but you can do it like a more contraction on the vertical direction. So you put 1/3 you put it, and then you bring it back. And then you have this model with the discontinuity. And the actual Lorenz attractor, what people do is they look what they call a transversal section. So it's a place where almost all trajectories are coming back, and it's going to look like a Lorenz map, a Baker map. So in those geometrical models of the Lorenz attractor, and actually in the concrete Lorenz attractor, if you see what is called transversal section, on the transversal section, we will see a picture very similar to a Baker map, which is dynamic with the discontinuity. So yes, the Baker map, you could consider that it's a kind of prototype model that happened in the Lorenz equation.
Mm-hmm.
And if you consider the Lorenz equation is a good model, the answer would be yes.
Yes, Masha?
Hi. You told that there were 10 years with no citation to that Lorenz theory, right?
I think there were very few, as far as I understand.
I wonder what happened after 10 years that people started to pay attention to Lorenz theory.
I'm not sure.
Any other theories evaluated or elaborated, or something special happened?
I think I knew the answer a few days ago because I read it on Wikipedia or somewhere, but I forget. Yeah, somebody. It was, I guess, somebody else who people were paying attention to did something.
Thanks.
Yes, DW.
Hi, I was just wondering if you could outline some of the references most relevant for the present talk and like some of the strengths and weaknesses of each of them.
Good. So I should mention all of the, if on the slides you click on the references, then it takes you to the back of the slides, which has the references in more detail, like this. I think all of the ones I cited are good. That's why I cited them. The book, let's see. Lorenz's paper is very good, as is the book by Strogatz. There's also the book by Ott, Chaos and Dynamical Systems. And the book by Dorfman, where also on focused on chaos and its application to statistical mechanics. Yeah, I think those are the main ones. Then this paper is also good, and I'll describe it somewhat later. There's also a book by Svetanovich, which is online, which is over 1,000 pages, called The Chaos Book, which I'll also reference later. It's complementary to the standard chaos text because it's more focused on developments in the last 20, 30 years on a specific kind of thing, which we'll discuss. I think that's everything.
Thanks.
Oh, yes. Another question.
Yes, so this is just another organizational question. So Jamal, will we be discussing any condensed matter examples beyond SYK?
No.
Okay.
Okay, let's start then. So the next topic will be pinball scattering. So this will be a different system that's chaotic and somewhat simple to understand. So the setup is the following. So consider the following experiment. There are 3 disks and a particle enters, and it enters at some impact parameter, and then it may or may not scatter off of the disks, or it could hit the disks a few times before exiting. There are a large number of possibilities, and then it comes out. So it goes in, hits the disk, maybe like this, and then it goes out. And so the question is this chaotic? So for most impact parameters, the particle will emerge rather quickly, because balancing between the disks multiple times seems unlikely and requires finely tuned initial conditions, because one would think for most initial conditions, most impact parameters, it just goes in, maybe scatters once or twice, but then probably leaves, because it's hard to keep bouncing around for a long time. So on that basis, one would be tempted to conclude that the system is not chaotic. So this problem was studied in the late 80s by Gaspard and Rice and others. It's nicely reviewed by Smolensky in Les Zouch lectures. And so what's striking is, so here is a plot of the outgoing deflection angle as a function of the impact parameter. So the horizontal axis is the impact parameter, and the vertical is the deflection angle. And just look on the top plot for now. So for some impact parameters, the deflection angle is fairly smooth. So this is just done by so this is just a collection of points, but they've merged together, so it looks like a line. But if you zoom in, you might be able to see that it's still points, and that's presumably reasonable, because if you well, at least for some range of impact parameters, it's clear you'll just miss everything, and so then that's pretty smooth. Though even if you don't miss everything, you could scatter off of one disk, and then that would clearly be smooth, and so on. The interesting part is, in this region of impact parameters, the deflection angle is looks like it can be anything. It looks highly erratic. And if one zooms in on this region, so just impact parameters around here, so here's the zoom in. So now we focus on impact parameters between 2.28 and around 2.36. What looks like the same structure repeats. So there are regions of regularity like these, and then there are again regions of chaos where you slightly change the impact parameter, and then you get any conceivable deflection angle. So clearly this is chaotic. I should mention that these papers were mostly interested in the quantum chaos aspect of this problem, but they reviewed the classical aspect. Perhaps the classical one was probably known much earlier. In any case, I took this plot from Smolensky. So if we now try to go back to our argument, because I argued in the beginning that it would be reasonable to say it's not chaotic. So it's true that for most impact parameters, the particle will emerge rather quickly, scattering off of only a few disks. So that's still true. But crucially, there exist infinitely many impact parameters that lead to the particle spending an arbitrarily long amount of time within the scattering region. So you can tune the impact parameters so that it keeps bouncing for an extremely long time before emerging. And it's these events that cause the erratic behavior, the possibility of spending a very long time. And the erratic behavior is just that an arbitrarily small region of impact parameters, range of impact parameters, just within here, will lead the particle to scatter into the full range of deflection angles. Good. So that's what one observes. One could say experimentally, numerically. So to start understanding this, the discussions of the discrete maps will be somewhat useful. So one thing to notice is that specifying individual trajectories is clearly challenging, and one might suspect that maybe that's unnecessary. So we could do the following: instead of specifying the full trajectory, which could be long and complicated, we're instead just going to label the disks by 1, 2, and 3. And instead of giving the full trajectory, we'll just state which disks the particle hits before it escapes. So for example, 1, 2, 1 means that the particle comes in, it hits disk 1, then 2, then 1, and then it flies off. Well, really it should go 1, 2, 1, and then go off. It's clear, at least potentially clear, that the number of such symbols grows exponentially with the number of disks that are hit. It's the reason why it's clear is because one, if there are n disks that are hit, then there are 2 to the n choices. 2 to the n because after you hit disk 1, you have to go to 2 or 3. You can't hit 1 again. The reason I say it's potentially clear is because it's not obvious every conceivable sequence of 1, 2s, and 3s that you write down is actually a realizable trajectory. So that depends on how you space the disks. So a simple illustration of the sensitivity to initial conditions. So this is a figure from Cvetonovich's book. So there are 2 trajectories shown here. So the solid one, it comes in, it hits 2, then 3, then 1, then 3, and then it flies off. So this one we would say has dynamics 2, 3, 1, 3. And then there's the dash line. So it starts off very close. So it hits 2, then 3, then 1, then 3, then 2. And you can see that at this stage already it started separating from the previous one significantly, because after it hits 2, it goes back to 3, then 2, then 1, and then goes off. So this is a clear illustration of the sensitivity to initial conditions. And we've also shown the symbolic dynamics, where instead of specifying the trajectory, which is hard, we just specify the sequence of numbers. Also, it's clear that the extent to which the initial conditions were closest to the number of numbers, the initial ones that match. So 2, 3, 1, 3 is common to both of these. So one can ask a further question, which goes back to something we mentioned, which is, what is the fraction of initial conditions that survive multiple scattering events? So we initially said that it's very unlikely to undergo many scattering events, and so one can make a plot of this, which I again took from Cvetonovich's book. So here we assume the particle first hits disk 1, and then the fraction of phase space, only a subset of that fraction will then hit disk 2, and another subset will hit disk 3, and the rest will just fly off. And then if one further asks, well, what about after hitting disk 1, then 2, what's the fraction of phase space that hits 1? That's just this sliver, and so on. So at each stage, the amount of phase space that leads to more and more scattering events, and specific ones, decreases. So now we can state a precise problem. So we want to compute something, and we want to compute something that's experimentally measurable. And a quantity that, an obvious quantity to compute is the amount of time that Good. So the fraction of initial conditions for which the escape time exceeds some time t, it decays exponentially with t, with some exponent gamma. And so a very precise question we can ask is, what's gamma? And this also seems like a reasonable, ultimately we're not interested in a particle bouncing off of 3 disks, we're interested in a collection of n particles, and there we'd be interested in the diffusion coefficient, and so this is a good warm-up. It's not at all obvious how to compute gamma. So there has been, in the last 30 years, a set of methods that was developed that goes under the name of periodic orbit theory or cycle expansion to address these questions. So I won't describe how it works. I'm also not an expert on it. So the methods are summarized in detail in Satonovich's book, which is quite long, but a quote from the beginning, which gives a rough summary. The motion in dynamical systems of a few degrees of freedom is often organized around a few fundamental cycles. These short cycles capture the skeletal topology of the motion on a strange attractor-repeller in the sense that any long orbit can approximately be pieced together from the nearby periodic orbits of finite length. So what's being referred to is that there exist periodic orbits which just bounce around between the disks, and for some initial conditions that you pick, you roughly move along one of these periodic orbits until you escape. And that's the basic idea that they use. A simpler example than this one for computing escape rates is in these one-dimensional maps that we discussed earlier, like the tent map. So now you say if you get above some vertical line, some higher than some value, then we declare that you've escaped. And so in those simpler contexts, it's easier to compute these escape rates. But it's been done for the pinball case as well. Okay, good. Are there any questions, comments? Yes. DW.
Do you know what inspired the particular example of pinball scattering?
Well, it's so if you take 2 disks, then you don't get chaos, so you need at least 3, and so 3 is the simplest number of disks. Why pinball scattering? Well, the problem one would ideally want to study is just a box of lots of balls which scatter off each other, so none of them are fixed. But that's too hard, so then one simplifies and reduces the number. But so now, so one is just left with 3 balls. It's a long, so there are a large number of examples. So this would be an example of single body chaos because the 3 disks are fixed. So it's in the same spirit of examples of chaos of a ball moving in some kind of stadium, in some kind of shape. And that's an example of chaos. So this is like that, but with 3 disks as opposed to some confined stadium. The reason I picked this one as an example as opposed to a ball moving in a stadium is that in high energy we compute scattering, and this is an example. This is closer to that because it's scattering. Yes, Enrique?
Though this model of billiards goes back to Sinai.
Yes.
So Sinai was studying, trying to prove the ergodic hypothesis on Lorenz gas, for instance. No? And in his case, instead of considering scatter in the plane, he was considering scatter in a torus. So it's a bounded region. And with one scatter, is enough to prove that it's chaotic, in particular ergodic. And the Lorenz model have so many scatter on the plane, there are infinitely many of these balls, and the people were asking if the particle eventually goes away or they remain in a confined region. And so further they have to study when you have only finite number. And what they prove is that, is what you say, is the majority of the trajectory, the Lebesgue measure of the majority of trajectory goes away. But there is a region that has a positive Hausdorff dimension. It's a Cantor set. It has positive Hausdorff dimension that remain there, and in this region is chaotic. But it goes back to the problem of the ergodicity of the Lorenz gas.
Good. I'll mention Sinai billiards closer to the end of the lecture. It will be, in the context of quantum chaos. Okay, anyone else, or we will move on? Okay, good. So let me move on. Good. So there's, so we've so far discussed, we've so far discussed highly chaotic systems, but a question that remains is how we go in between what we know, which is integrable systems, and these chaotic ones. So more precisely, for an integrable system, there are n degrees of freedom, and then there are n conserved quantities, and the motion in phase space has to preserve those conserved quantities. And so as a result, the trajectory only explores a subset of phase space. So it lies on an n-dimensional torus. And if n is large, it's clear that this is an exceedingly small subset of phase space. So here's a picture of a torus moving along it. On the other hand, for a strongly chaotic system, the trajectories diverge from each other. We expect no conserved quantities aside maybe from energy. And so we expect that the trajectory will eventually explore all of phase space. So both of these statements one can make without knowing much of anything, at least to some degree of confidence. However, the question is what lies in between. So how do we get from integrability to chaos? And are most systems closer to integrable, or are they closer to strongly chaotic? So we still have unanswered the question that was posed in the beginning, which is that the solar system, we can't solve it, but it appears that our intuition from integrability is fairly good. On the other hand, a box of gas for which we do statistical mechanics, that we would say is ergodic, but we haven't explained how to get from one to the other. So a nice example is the Henon-Heil system. So so in this section, I will only slightly answer these questions. And what I'll do now is just present some plots. So the Henon-Heil system, so they took the following Hamiltonian. So one can think of it as motion in two dimensions or two particles. So px squared plus py squared over 2, and then there's a potential x squared plus y squared, and then there's a nonlinear term, x squared y and minus 1/3 y cubed. So the phase space is 4-dimensional, xy, px, py, and energy is conserved, so the motion is confined to constant energy surfaces. And so we'd like to ask, suppose we pick some initial conditions and evolve, what does the trajectory in phase space look like? So the first thing we would try would be to just solve the equations of motion ourselves, and we find that that's challenging. So then we do it numerically. So plotting phase space by itself is somewhat challenging because of the number of variables. So one thing one can do is instead plot the Poincare section, which at least for systems like this with 2 degrees of freedom is useful. So we intersect the phase space trajectory with a codimensional surface. So for instance, we pick the plane x equals 0. So there'll be a trajectory moving in phase space, and whenever it hits x equals 0, we'll record that point. So that's the only information we're recording. whenever the trajectory is away from x equals 0, we don't care. We just care when it passes x equals 0, for example. And then we're going to make a plot of y and py. So we're going to be making just two-dimensional plots. And since energy is conserved, it makes sense to specify the initial conditions in terms of y at time 0, py at time 0, and the energy. So this is what Hino and Hales did. They took various energies and made Poincare section plots, which look rather remarkable. So I've just copied their plots. So they started at low energies. So this is for energy equals 1/2. And at low energies, you get what you expect. So I should note that they've combined multiple initial conditions. So if you pick some particular initial conditions, you get this oval. And then if you pick different initial conditions, you get this one, and so on. So they picked what they call the representative subset of initial conditions. And then they put them all on one plot. So the trajectories look regular, like we expect with our integrability intuition. And on the other hand, we don't really know how to solve the equations of motion, but this isn't surprising because at low energies, we only explore the potential near its minimum, and by Taylor expansion near the local minimum, the potential looks quadratic, and so it's integrable, and so that explains why the trajectories are regular. So that's not too surprising. Then they took high energies. So energy equals 1/6 is high. And again, did the same thing. So again, this is the Poincare section of y versus y dot. So we're just intersecting the motion in phase space with the plane x equals 0. And what one finds is just a bunch of, for the most part, just a bunch of scattered points. And this too is what we expect. We're at high energies, the potential is nonlinear. We're not close to integrability. And so we expect with our ergodic intuition that the trajectory should fill all of phase space. And the filling all of phase space when we take the slice just should appear like a bunch of scattered points, which essentially is what we get. There are a few islands of regularity, but for the most part, it's just scattered points. Okay, so neither of those two things are surprising. What's more interesting is the result at medium energies. So energy is 1/8, recall, so low energies was 1/12, high energies was 1/6. At E equals 1/8, they find the following plot. So there's a combination of regular motion. So if we picked these initial conditions, we get these trajectories which look like we expect for integrable systems. As you go out, they start getting slightly deformed, but that again is not too surprising. But then in this region, then there are some choices which just give these scattered points. And in fact, there's incredibly, well, this is what they found, and there's incredibly intricate structure in this, which is discussed in this book by Lichtenberg and Lieberman, which I won't comment on. The only thing I will say about this is the result looks remarkable, but it's easy to reproduce oneself because now one has Mathematica. So we can just have Mathematica solve the equation and take the Poincare section and make the plot for various. So this is at medium energies for various initial conditions. And so I just made these plots. So this is for one choice for initial condition, and these are for two others. So you can see that this is precisely what they have here. So this is one choice, and this is the second one, and the third is just the scattered points like that. Good. So I didn't explain much with those figures. It just illustrated that well, certainly something. The transition from integrability to chaos is certainly interesting. So to do this more systematically, it makes sense to start with an integrable Hamiltonian and then change the Hamiltonian by adding an integrability breaking perturbation and then increasing its coefficient and seeing what happens. So let me briefly discuss that. Are there any questions? about Henon-Hiles? No, good. Okay. So this problem is very difficult, as one could imagine. There's a somewhat elementary discussion in the book by Tabor. So the problem was studied by many. Yes. Okay. So this anyway, there's a somewhat elementary discussion in Tabor, which is what I'll follow. So let me remind you that for an integrable system with variables p and q is position, p is momentum, the equations of motion are the standard ones. Q dot is the hdp, p dot is minus the hdq. And usually it's not so easy to solve these. However, if the Hamiltonian is independent of q, for instance, for a free particle, then we notice that p dot vanishes, so p is conserved, and then this is easy to solve. So that's an integrable system. Now, if suppose we're given some Hamiltonian and we're told it's integrable, it probably won't be in such a nice form of immediately being in this form. We can integrate the equations of motion, so we have to change variables, do a canonical transformation in which to variables in which the above was true, and these are the action angle variables. So instead of using p and q as the momentum position, we use the action and angle variables, where the action is the integral of p dq, and theta is the angle variable, is the canonical conjugate. And in these variables, if it's an integrable system, then h only depends on I, and so then the equations of motion are again simple, and we can solve them. So all we're doing is changing coordinates to bring it into the form where we can easily solve it. So one thing to notice is that so theta dot is the HDI, which we're going to call omega of I. For a harmonic oscillator, omega of I is just I, the frequency of the oscillator. But this is a special case. So generically, omega of I is actually a function of I. That's important to remember. Good. And then to relate, so what I'm reviewing is just standard mechanics. To relate the action angle variables to the original variables, there's a generating function, and then we solve the Hamilton-Jacobi equations. Just the normal procedure. So now we can get to the question we wanted to answer. We start with an integrable system, h naught of p and q. We know it's integrable. And then we add a small perturbation. And the question is, can we use perturbation theory to solve the equations of motion of the perturbed system? So in the very beginning, we said that we are used to studying integrable systems and not chaotic ones, because we realized that the simple systems we're studying are not generic, but we hope we can do everything else by perturbation theory. So now let's try to actually do this. Also, I've switched to boldface to indicate vectors, so we'll have multiple variables. So there's slightly more detail that I want to go through, but the point is, we said our h naught, our starting Hamiltonian, the unperturbed one, is integrable. So we change to action angle variables where it's just a function of the actions I, and so we change it for everyone. And so this is our Hamiltonian, and now our goal is to find new action angle variables, I prime theta prime, in which the new Hamiltonian is theta prime independent. So if we succeed, that will mean the perturbed Hamiltonian is integrable, which will mean that there's some more integrable Hamiltonians that we didn't initially know that were integrable, or maybe there are just a lot of integrable Hamiltonians. And in any case, if we're just going to try to do this perturbatively and see what happens. So so our goal will be to find this generating function to do this transformation. So we're just trying to, so the viewpoint we're taking is, we start with an integrable system, we perturb it slightly, we say, okay, the only way we know how to solve things is by let's assume the new thing is integrable as well and just do our procedure of integrating the integrable one by finding the generating function and changing to these action angle variables. So we're just going to try to implement that. And to simplify the story, we're just going to perturbatively start solving the Hamilton-Jacobi equations. So I'll skip the details. Let me skip to the answer. So the result for the perturbed generating function that we need to find, the generating function which generates the transformation between the old and the new action angle variables is given by this sum. So omega naught of I are the frequencies of the unperturbed system. And HM1 are the Fourier modes of the perturbed Hamiltonian. So we've just written it as a Fourier series. So this is the answer. And if we look at this, if the omegas, if the frequencies are, so again, to remind you, if our unperturbed system was just our harmonic oscillator, for harmonic oscillator, the frequencies don't depend on the action, but that's very special. Generally, the frequencies depend on the action. So on these actions, so once we pick some specific initial conditions, then we'll have some specific values for the frequencies, but different initial conditions give different frequencies. And so these frequencies, this is a vector of frequencies. And if they're all irrational, then there's no mathematical problem here, because then this is never zero, the denominator. There could be a physical problem because even if they're irrational, this could get small, and then this first order correction could get large, and that means we need to keep going to higher orders. But at least for small m, for small integers, there's no problem. Here there's a sum. On the other hand, if they're rational, then we have a zero in the denominator, and then we have a problem. And then one says that one has resonant tori and that they're destroyed by the perturbation. And those trajectories can now wander over a larger segment of phase space. And so there's now a difficult problem of what we're supposed to do. So all we did was we said, we think we can solve things by perturbation theory, let's try. And then we run into this issue, which it's not clear how to deal with. So this was dealt with by the KAM theorem, which for which I only know the slogan. And the slogan is that if the magnitude epsilon of the perturbation is small enough, then most of the tori survive. So to be slightly more precise, for n equals 2, if there are 2 degrees of freedom, so there are 2 frequencies. Two frequencies would mean like the Earth is, well, anyway. If the ratio of frequencies is close to rational, where close is defined by this inequality, then the torus is destroyed. And if they're further from rational, then it survives. For us, just looking at this without knowing anything, this was hard to assess because rationals are close to irrationals, and it wouldn't make sense for us to say it's just if it's irrational, then we're okay, because we're not really okay. But this is a precise statement. So because this power, so if it's close to rational, the rational number R over S, then as destroyed, notice that this power is 2.5, which is greater than 2. And so that there's still a finite measure of ratios omega 1 over 2 that are preserved. And this means that as one takes epsilon to 0, the perturbation gets small. That's the origin of the statement that most of the tori survive, most of the tori being most of the ratios omega 1 over omega 2. Good, so that's the theorem. And usually one starts with the theorem and then one has the illustration of the Untitled, but I switched the order, and we already saw the theorem in action when drawing those phase space plots for Untitled. So this is in part an explanation, the start of an explanation of what was happening. Good. Questions, comments? Yes, Enrique.
So in the model that the Henon model.
Yes.
For all parameter always there exists an elliptic point. I don't know. This is the question.
What do you mean by analytic point?
Elliptic. You have a fixed point in the middle when you put the one that they are close to integrable. Now the picture that, so you have this fixed point, which is an elliptic point. And then you were making like a higher energy, and still there is like a small circle, and inside there is a fixed point. The question was, for all level of energy, if always there is a fixed point which is elliptic.
I see, I see.
Elliptic means that the eigenvalues of the derivative is, they are on the Newtonian circle. I don't know, maybe it can be proven analytically that for all the energy level, always there is an elliptic point. Exactly in this region in the middle, not the one that they cross the line, not this one, but the one to your right.
This one.
Yes, that when you refine the picture with higher energy level, they still appear.
Yeah. So here I went to very high energies, and it's still here.
Yeah. So because if always there is an elliptic point for all energy level, around the elliptic point you can apply the Kn theory. So always there will be some small region where you have some Kn toroid, in this case, our circle that remains.
Good, exactly. And that would mean that
you can feel almost everything, but you are not reaching the region nearby the elliptic point.
Good. I should point out that here it's a little difficult to go to. You can't go to arbitrarily high energies because the potential is unbounded from below. So this is sort of as high as you can go, because then you run off. This is an unfortunate.
Okay. So, but anyhow, so if you prove so for some way that always there is an elliptic point, or at least in certain range there is an elliptic point, then you cannot have a trajectory that is going to be dense, because you cannot reach the region nearby the elliptic point, because you can apply the other theorem that you were mentioning, the Kn.
Exactly. Yeah. And right. And so that's why we have here, we say essentially fill all the allowed phase space, but not completely, because right. Good.
Good. No, thank you.
So Vladimir, I can't raise my hand, I think. In the statement of the KAM theorem, you have this factor of s to the 2.5, and you noted that that is what makes the finite fraction of things surviving.
Yes.
So I think I can go through the argument in my head as to why, I mean, it's 2.5 versus 2, which has to do with computing an area in the neighborhood of the point.
Yeah.
Can you just unpack that for us? I'm guessing I'm not the only one.
Good. It's just, I'm just saying that if you do the integral of, I'm just saying it's equivalent to a simple statement that the let's see. So if it was less than 2, then that would be problematic, but greater than 2 is fine. I guess the argument is presumably you integrate this power and then multiply by s. So so then you, with the fraction that you end up with, if that power is, the question is if that power is positive or negative. I feel like that's as much as I can say without the picture.
Good evening or afternoon or morning. What do you mean when you say that the torus is destroyed?
Good. That's a good question. What I mean is, well, there are several levels of answering. The first is in this formula we have a problem, but more precise, or in terms of the example. So we had some regular trajectories. So we picked some initial conditions. We got a regular trajectory. Then Big Dipper, we also got a regular trajectory and so on. So that's for some low energy. Now we start increasing the energy, and
Right.
as Enrique emphasized, this one survives. It's still here. But then the trajectories that were here, now they're gone. Instead, you just get scattered points. So if you can somehow visualize phase space, initially everything was confined. I'm moving in the wrong direction. Initially, everything was confined to move on this n-dimensional torus, which is a small subset of the two n-dimensional phase space. And then, the frequencies of these tori are functions of the action variables, so they depend on the initial conditions. And so for some initial conditions, you hit a frequency which we say does not survive, and that means now the trajectory in phase space is not confined to this torus. It can explore a broader region of phase space. If all the tori were destroyed, if you pick such initial condition that all the tori are destroyed, then you can go into the full 2 n-dimensional phase space. You're not confined to this n-dimensional torus.
I see. A follow-up question would be, so why are we considering a tori in the first place? It's a 4-dimensional phase space. Now we have constrained X because we've taken the Poincare section, which means that we still have three degrees of freedom to consider. Now a torus implies that it's a 2D surface. A torus also has additional constraints of periodicity involved. So why are we using that to analyze this problem?
Good. So in doing this, we're not going to use our initial variables of P and Q. We switch to the action angle variables, which are periodic.
Right, I see.
So that's the first thing. In terms of the Poincare section, so I stopped. So there was a question one could have asked earlier, which is really the question is it ergodic or the tori? What happens in the full phase space? Why is the Poincare section representative? In other words, if I got an ergodic looking picture in the Poincare section, does that mean in the full phase space it's ergodic or not? And I guess there's a theorem that says that it is.
I see.
There's another question one could ask, which is the Poincare section. It's helpful if one only has 2 degrees of freedom, like this thing we were studying, but if one has more, then it's not so useful because it only reduces you down by 1 dimension. So if I had started with a system with 10 degrees of freedom, I take the Poincare section, I still have far too many to draw.
I see. Okay, thank you. Just one more question. The perturbative expression for S for the action that we had obtained, that looks, so that features an omega naught. So this, for some reason, it reminds me of an equispaced, of a quantum harmonic system with equispaced levels, with omega naught being the frequencies there. So is there some connection that one can think of? Because in the perturbation theory that we learn, we see that the denominator usually features a difference of energies, right?
I see what you mean. Yes. We're doing first order. Yes. So it occurs in both places because, it occurs in both places. Well, it appears in the it appears because, so we took a derivative and that brought it down. We're doing perturbation theory in both. Good. We're doing perturbation theory in both cases. In one case, it's with the Schrodinger equation, and the other case, it's the Hamilton-Jacobi equation.
Right. So no. So like that I got, but the thing that struck me was that there seems to be some omega naught, which defines the level or the spacing of the energies.
Omega naughts. Good. The omega naughts are the frequencies. So they're the. Once we change to, so more precisely, they're defined as dH naught di. So once we change action angle variables, they're the frequencies at which you orbit these tori. They're not energy levels. They're just.
I see. So, okay. So one comment on what you are saying is you go to the lower energy level, you are filled by circle. In the picture that Vladimir was putting before, we can see in the Enon case. Can we see? So, okay, so you have this whole circle, and it will be in certain area fulfilled by circle. And so the dynamics are moving around the circle, and in certain circle they are rotating. It's like we are rotating the circle either with the rational frequency and on irrational frequency. When you're rotating with the rational frequency, you have what is called a periodic point.
Right.
And the derivative on the periodic point have to be 1 because you are confined in the circle. But if it's irrational, then if you perturb, automatically the derivatives are going to be different than 1. It will have one eigenvalue smaller than 1 and one larger. And this implies that the circle, the tori or the circle are destroyed.
I see.
And on the other hand, when it's irrational, so you have the chance that in this formal series that he is describing, maybe you have convergence, but you need a stronger condition, and this is what they call the Offendine condition. And it's related to the problem that was mentioned before about the 2.5 power. You have to be larger than this number. But the majority of the circles have this type of property, and then this formal series is going to converge.
Good. Okay, let me move on to the last topic of.
Thank you, sir.
Yes, thank you. Of quantum chaos, few-body chaos. So I'm only going to briefly discuss chaos in quantum mechanics. So there are two classes of questions we can ask. One is semi-classical and the other is fully quantum. So just to remind you, in classical mechanics, a particle follows a definite path, and that path is found by extremizing the action, which is a function of the path. In quantum mechanics, a particle explores all paths, and each path is weighted by the action. So this is the Feynman path integral. And in the limit of h bar goes to 0, in the classical limit, the sum is dominated by the classical path, the one that extremizes the action. And the question of semi-classical quantum chaos is the question of how chaos in classical systems manifests itself in the quantum system. So to remind you to take the semi-classical limit, so if we have a quantum system, which we obtain from by quantizing the classical system, we can get back to the classical limit by forming wave packets out of high momentum modes. And then there's a range of interesting questions one could ask. If one has a classical system, one quantizes it, what are the quantum, and that classical system was chaotic, what are the quantum effects? We won't discuss that. One comment I do want to make is that in the old literature and in some new literature, it's sometimes stated that linearity of quantum mechanics is inconsistent with chaos, because after all, one says chaos requires nonlinearity, but the Schrodinger equation is linear. In other words, one says that the evolution of a state is unitary, e to the minus iht psi of 0. And so the overlap of two states, overlap of psi of t and chi of t, is time independent. And therefore, one would be tempted to say that a small perturbation, so changing psi to psi plus epsilon chi, doesn't grow with time, as would be needed for chaos. So all of this is technically true, but it's false. The conclusion is false because it has to be, because the classical limit wouldn't make sense. And so the important point is that two quantum states can have almost no overlap, but still be physically similar. So one can have two wave packets, as I've drawn here. They're very close in phase space. Out of the entire phase space, they lie very close. But their overlap is essentially 0. So the reason this argument is false is because one is not doing the physically correct perturbation. Nevertheless, so there's the question of semi-classical chaos where we just take where it says where we just try to find how chaos impacts how the quantum mechanics of a classically chaotic system looks like. But then there's a deeper question, which is just to define quantum chaos without the crutch of classical mechanics. And the natural phase space, the natural state space of classical mechanics we know as phase space. All our discussion was interwoven with space, but for quantum mechanics as the eigenfunctions and eigenvalues of a Hamiltonian. When we learn quantum mechanics, the thing we always compute is the eigenfunctions and eigenvalues of a Hamiltonian. So when we quantize, we take a classical Hamiltonian, we replace the momentum with ddx, and then we solve the Schrodinger equation for eigenfunctions and eigenvalues. So that's what we're used to doing. And the connection between, so that's very different from anything we do in classical physics. The connection between that and classical physics is Bohr-Sommerfeld quantization. Integral pdx is 2 pi times an integer, which is what we initially learned, which is what was developed in the 20s before quantum mechanics, before the full quantum mechanics. And this is valid at high energy levels. And this roughly gives the right answer. This formula might be more familiar in the context of the WKB approximation. However, one thing to notice, which is a little surprising when one first realizes it, this formula only applies to integrable systems, because you need there's a circle here, you need a closed curve. And so for chaotic systems, it's unclear what we're supposed to do. So one could say that there's nothing you can do. You just need to solve the Schrodinger equation. And that's the situation. That's a plausible answer. However, one would still like some kind of connection between the spectrum of energy levels in the quantum system and something classical. It's hard to imagine that connection that exists for integrable systems just completely goes away once you make the system slightly non-integrable. And indeed, trace formulas, the generic name, is what connects the spectrum of the Hamiltonian to classical periodic orbits. So Gutzwiller gave the first general trace formula. In effect, he took the Feynman path integral and expanded around the semi-classical paths, which we're used to doing, but in some sense he did it more carefully. And since his work, significant progress has been made. This is described in detail in Cvetanovich's book. What seems like a remarkable achievement is so they derive the spectrum of collinear helium. So this is the Hamiltonian. So it's a 3-body problem. So one naively has no clue how to proceed, but they derive the spectrum of collinear helium using quasi-analytically, quasi-numerically, using classical orbits, not by just solving the Schrodinger equation on a computer. But I won't discuss this. Good. So so that takes care, to the degree I discussed it, of semi-classical systems. But we know that there are many quantum systems that have no classical analog. For instance, a spin chain of spin 1/2 particles. So this is my condensed matter application. And indeed, one might argue that from perspective of modern physics, these are the most interesting systems. And so without the crutch of classical physics, there's a question of how is one supposed to understand chaos? The simplest answer would be that there's nothing to understand, that chaos is a classical concept. And so one shouldn't be asking the question of quantum chaos away from some kind of semi-classical limit. However, this isn't a particularly useful answer, since we know that thermalization happens in many quantum systems, and so there must be some underlying microscopic physics responsible for that. And so we need an inherently quantum understanding of chaos, which doesn't rely on phase space. Presumably something that's formulated in the natural language of quantum mechanics of eigenfunctions and eigenvalues. So leaving aside chaos for 2 minutes. So in the 1950s and after, nuclear physicists were interested in the excitation spectra of various heavy nuclei, like uranium-238. So this is a quantum many-body problem. So solving the Schrodinger equation is kind of hopeless. Nevertheless, one wants to know what the spectrum is. And so the proposal that was made in a very rough form by Wigner, Dyson, Mehta, and others which is discussed in this book, was roughly the following. Just so let's think of the Hamiltonian as a matrix, which if the Hilbert space is finite dimensional is a good thing to do. And the Hamiltonian that we care about for these heavy nuclei, it's incredibly complicated. There are many particles, they're all interacting. So what we're going to do is we're going to get rid of that Hamiltonian and instead just take a random matrix and pretend that's our Hamiltonian. And we'll hope that for some questions, this gives the right answer. This somewhat has the flavor of what we do in statistical mechanics to an extent. So doing this, what could one compute to check? So a quantity of interest is the distribution of spacings between nearest eigenvalues. So you take one of these heavy nuclei, you imagine computing all the energy levels and then looking at the spacing between the nearest energy levels. And this was done, and this is a plot of the spacings, of the distribution of spacings. And these thin things is the data, and the curve is the fit to random matrix theory. GOE stands for Gaussian orthogonal ensemble, which is the correct distribution one should be using for random matrix theory. Good, so it appears to work well here. Okay, good. So now, that was, it's unclear why I'm discussing this and what this has to do with chaos. Well, it's only partially unclear because one might say most likely these are complicated systems, so they're probably chaotic. But to make contact, we'll go back to classical chaos. So Sinai's billiards, Enrique mentioned it. So this is a classic example of a chaotic single body system. It's somewhat like the example we discussed, the ball scattering off of 3 disks, but different. So here the particle is confined to this square and it's excluded from this circle. So it bounces around, hits the circle, bounces here, and so on. And so it's straightforward to take the system, quantize it, just solve the Schrodinger equation, and look at the energy levels. So that's what's going to be done. So this was done in the seminal paper by BGS in the 80s. And what they found is that the nearest neighbor level spacings, the same quantity, you look at the energy levels and compute the spacing between nearest neighbors and plot the distribution, it's the same curve. It again agrees with random matrix theory GOE. This picture here is Sinai's billiards, but they cut out a piece of it because of the symmetries, and they use that. Good. So that was the result, and so to quote what they said. So the result seems somewhat surprising. To quote what they said, they say the basic hypothesis leading to random matrix theory have always been put forward by invoking the complexity of the system. In other words, it has been taken as essential that one is dealing with a many particle system. Our results indicate that this is by no means a necessary condition. Indeed, the quantum chaotic systems with 2 degrees of freedom studied here, a 1 particle system in 2 dimensions, shows also GOE fluctuations. That's random matrix theory. And then BGS conclude with the BGS conjecture, which is that the spectra of systems whose classical analog is chaotic will show the same fluctuation properties as predicted by random matrix theory. Good. So let me end with that. Given the time, I won't summarize. I'll just I guess the summary of given the time, let me leave it at that and see if there are any questions. Yes, Enrique.
So I'm still confused on the quantum chaos and what is expected. So you say when you have a classical system and you are going to quantize it.
Yes.
And you were saying, well, when the system is integrable, then it's easy to understand the spectrum based on the property of the integrable system. This is what you say. I don't know. This is the question, the first one.
So to answer well, if it's integrable, I can just compute the spectrum.
Okay,
myself.
perfect. Good.
So there's there was
the question. Sorry, and so perfect. I understood this part. Great, thank you. And the second part is, so what you want to do is try to get some information of the spectrum based on the dynamical property of the classical system if it is chaotic?
Good. So good. So for the first half of the chaos talk, the semi-classical quantum one, which I think is the one you're asking about, this may not be what you're asking, but it was a question I always had, which is if suppose the system is not integrable, so I can't solve. I don't know how to solve the Schrodinger equation, so I don't know what the spectrum is. So what am I supposed to do? And you could say you just need to solve the Schrodinger equation. How you solve it, just put it on the computer and solve it. And you could say that's fine, but I just want to just get some sense of the energy levels. Is there maybe the high energy levels? Is there something I can do? Something that replaces Bohr-Sommerfeld quantization, which allows me to make contact with classical physics. So because of Bohr-Sommerfeld, if I have a classically integrable system, I don't actually need to solve the Schrodinger equation for the high energy levels. I can just apply Bohr-Sommerfeld, and that tells me the answer, which makes sense because at high energies, you expect that the system is essentially classical. And so the question is, for a chaotic system, what replaces Bohr-Sommerfeld to connect with classical physics? And that's the thing that the Gutzwiller trace formula, and in more precise and computationally useful ways, this periodic orbit theory does. It relates this quantum problem to a classical question.
Okay, good. And how random metric theory fits on this approach?
Good. So I presented them as two separate things. So that's one thing you could ask. On the other hand, you could take the viewpoint, if you're not a semi-classical physicist, you're doing quantum condensed matter in the modern era. You could say you really don't care about semi-classical systems. You want fully quantum systems, and you don't want to connect with classical physics. You just need to know what the energy levels look like.
Okay.
And then you say, and then the idea going back to the 50s was the Hamiltonian is so complicated, we just replace it by a random matrix. And then the recognition was that, so perhaps to summarize, there are some universal properties such as of chaotic quantum Hamiltonians, such as the distribution of level spacings between nearest neighbors, which you can state even if you don't know how to solve your particular Hamiltonian. So we showed it for Sinai's billiards, but if you took some other classically chaotic system that you know is classically chaotic, and you asked, can you tell me anything about the spectrum of the Hamiltonian? This is one thing that you could immediately say, and to the extent that the conjecture is true, which I guess is fairly confident is true, you would know this thing about the distribution of spacings between nearest neighbors.
So if the system is a quantum chaotic system, no? Even if you are formulating like the quantization of a chaotic model, can you say something for the spectrum? So the spectrum is a Cantor set.
Not the spacings between levels, but
yes,
the actual.
At least some information that is not a connected set. They have holes. It's a Cantor set.
I'm not sure, but the levels. So the levels are discrete, are usually discrete anyway, because.
Well, not necessarily, no, because the spectrum is not necessarily the eigenvalue. No, the spectrum and operator, you have also another elements, no.
I just mean the eigenvalues. I just mean the Schrodinger equation. You put, like the billiards. There's eigenvalues, just the energy levels, and they're discretely spaced. In terms of the actual mean values, that I don't think there's any universality claim.
Okay.
Yes. Deep.
Sorry. So yeah, my question was that in the graph which showed the eigenstatistics, there was one curve that there was a Poisson distribution as well.
Yes.
So what does that signify? Like what kind of a system does that characterize?
Yes, good. So the slogan is, if it's integrable, then it should be Poisson, and if it's, which is this thing, And if it's chaotic, then it should be random matrix theory GOE. So Poisson would mean that the energy levels are uncorrelated. So
I see.
Now you might ask why is that correct for an integrable system? So if you imagine that your system, so this goes in the name of the Berry-Tabor conjecture. So if you imagine that your system is just a bunch of harmonic oscillators with different frequencies. So the energy is some ni omega I, where I runs from 1 to k, where k is the number of harmonic oscillators. Then there's sort of no correlation between the energy levels. Because to get from one level to the next, it's not the case that you just move one oscillator up by one. It could be you change the occupation numbers of the various oscillators. So it appears that there's no correlation between them.
So you speak about correlations in your answer. As far as I know, even disordered systems have uncorrelated levels, which implies that you cannot jump from one level to another. The particle gets stuck. So will that also have a similar statistic? Will that also have a similar graph for the eigenstatistics?
Good. So you say if we take a system with disorder, which one will it be? Will it be Poisson or random?
Yes, because in classical classical systems, I would guess that if I have disorder, there would be more scope for chaos in some sense. But quantum mechanically, it leads to lack of motion. I mean, the mobility goes down and stuff.
Good. So if we could be slightly more specific. So in fact, the Anderson in fact, the opposite is somehow the opposite happens, that Anderson localization, Anderson studied the question. This might not be what you're asking, but there.
No, I'm asking this only, yeah.
Good. So if you take a sufficient amount of disorder,
yeah,
the more disorder you take, the more localized it is. So the closer it is to integrable.
I see. So their disorder introduces integrability, and okay. Can one talk about a classical limit of that model? Again, this relates to my question about how disorder in classical systems would increase the chaos. I mean, it would allow for richer trajectories in a sense. Again, I'm not very well read on this, so yeah.
But so tomorrow we'll have a disordered system.
Okay, cool. Yeah. Thank you.
Yes, DW.
So on this plot, you show Poisson and GOE. Where do GOE and GSE fit into the picture of quantum chaos?
What's GSE? What's the S? Oh,
the unitary ensemble, and I guess the symplectic.
Good. So there's GOE. So there's orthogonal, unitary, and symplectic. So the reason we're picking GOE is because we have a time symmetric. So it depends on the symmetry. So if you have a time symmetric, then you should pick time symmetric Hamiltonian. Then you should pick GOE, which is why they pick GOE. And if you don't, then you pick the other ones. The GOE is the relevant one for. It's the one, since Sinai's billiards is time symmetric, that's the relevant one.
Okay, let me do my chairmanly duty. We should thank Vladimir and thank all of you for joining us. We're going to reconvene again tomorrow at the same time, 11 a.m. Eastern. We hope to see all of you again. Thank you. Thanks again, Vladimir.
Cool, thanks.